This is chapter 15 lecture. We're going to talk about electrolytes, acids, and bases. And it will be a shortened version of what you guys have seen in class already, and then covering the end of the chapter. Hopefully this can be more of a cohesive review of the material. I know the end of the semester can be rough, and there's a lot that tends to be piled on at the semester at the end, so you guys are done with everything except for exam 4, so that's all you gotta worry about. So let's get to it, and we'll finish chapter 16 we'll do on Tuesday, and that's going to be a pretty quick lecture. Alright, so we started with this review of chapter 8 material and chapter 12 material. Just right here, because these are going to apply to this section, as well as some chapter 14. So I asked you to classify these two reactions, and if either was a double displacement, to tell me which type. The first one is a single replacement. It's just the single magnesium takes the spot of the hydrogen in this reaction. The second reaction was a double displacement, where the pairs of molecules swapped partners, and this was specifically called an acid-base neutralization reaction. The second question I asked was, how would you describe what is occurring to the acetic acid as shown below when it's placed in water? So this is a throwback to chapter 12. We've got acetic acid as the solute. Water is the solvent. We have a solution of this. And when acetic acid is placed in water, you'll notice that where there were 3 hydrogens attached to these COO groups, now you have 3 COO minus groups and 3 protons. So when acetic acid is placed in water, it dissociates. So acetic acid dissociates when dissolved in water. So an important distinction here between dissolved and dissociates. When we say something is dissolved, we're saying a solute is placed into a solvent, and only the intermolecular forces between the entire molecules are disrupted. If something also then dissociates, we're saying a part of that molecule, so in the case of acetic acid, breaks off. So we're here, intermolecular forces are disrupted. Here, ionic or covalent bonds are disrupted. To give ions. And both of these concepts, so acid-base and this idea of dissociation when you dissolve something in a solution of water, chapter 15 goes more in depth on both of these. So by the end of chapter 15, I would expect you to be able to complete this checklist. We're going to go through each of these things. You can practice it in the homework and use this as kind of a study guide on concepts that you should know for chapter 15. And since I saw a lot of people were kind of in the middle or thumbs down when I asked how you're feeling about this chapter, hopefully this will give you a good gauge on what you should focus on when you study. So a reminder, section 1, first let's just talk about what electrolytes are before you start identifying what is a strong or weak electrolyte or a non-electrolyte. So an electrolyte, as we stated, is a solute that dissolves in water. So water is our solvent. And dissociates. So it dissolves, it breaks intermolecular forces, and you get the individual molecules floating in water, and then those individual molecules dissociate into ions. They're covalent or ionic bonds that get broken and disrupted, and it turns into ions. That is the definition of an electrolyte. A non-electrolyte is a solute that dissolves, so its intermolecular forces are also disrupted. Again, water is the solvent. But for non-electrolytes, they do not dissociate into ions. So no covalent or ionic bonds are broken for non-electrolytes. Usually, compounds that dissociate tend to be ionic compounds, and compounds that do not dissociate tend to be molecular compounds. So we would say ionic compounds are usually electrolytes, and molecular compounds are usually non-electrolytes. Now there's an extra bit to these definitions, and you all can go through and do questions 1 through 3 on the worksheet. So pause this video, do questions 1 through 3 on the worksheet, and then come back and play it, and we'll summarize what you learn about your conclusions from questions 1 through 3 and how that might add to our definitions of electrolyte and non-electrolyte. So based on questions 1 through 3, hopefully you've paused the video and tried them. You learned that electrolytes, a new phenomenon that you learned about was that they can carry electrical charge. And the fact that they carry electrical charge comes from their ability to dissociate into ions. Ions. We determined they are ionic compounds. And from the worksheet, we also encountered a scenario where sulfuric acid, a molecular compound, was actually able to carry electrical charge and therefore is considered an electrolyte. So sometimes there are a select few of molecular compounds are sometimes molecular compounds that are considered electrolytes. From the worksheet, the new information about non-electrolytes that we learned was electrolytes. They cannot carry electrical charge, so they will not light a light bulb. And then they do not dissociate into ions when placed in water. So in water up here, and they do not dissociate. And are usually molecular compounds. So we can amend our previous definitions just by adding the information we learned about electrical charge. And here non-electrolytes cannot carry electrical charge. So those are our full definitions of what an electrolyte is and what a non-electrolyte is. So now we can go on to describe strong and weak electrolytes. What's going to come into play here is from chapter 14, where we discussed equilibrium constants. We stated that if KEQ was greater than or equal to 10 to the third, you have a favorable reaction where all product is formed and no reactant is left over. If you're between 10 to the minus 3 and 10, but above that, but below 10 to the third for KEQ, then you have a range. And that range is as follows. If KEQ is greater than 1 or closer to 10 to the third, you have more product, but still an appreciable amount of reactant left over. So the more product will be formed. If KEQ equals 1, that's a neutral reaction, which is very rare, but it does occur. And that's when you do have equal amounts of product and reactant formed at equilibrium. But again, at equilibrium, the amount of product and reactant formed is constant and not always necessarily equal. It is very rare to have a neutral equilibrium. And then when equilibrium is less than 1, your equilibrium constant, you have unfavorable. And so you have only a little bit of product being made, but most of it stays as reactant. And then once you get below 10 to the minus 3, it is considered unfavorable as well. And we say the reaction does not go to completion at all, and you just have a bunch of reactant in your flask. So we're going to use these equilibrium constant concepts and guidelines to figure out what a strong electrolyte is. So the definition of a strong electrolyte is something that completely dissociates into ions when dissolved in water. Again, remember, dissociates means we're breaking covalent or ionic bonds to get ions. Dissolved means we're disrupting only the intermolecular forces. A weak electrolyte only partially dissolves or dissociates. It might fully dissolve, but it only partially dissociates into ions when dissolved in water. For strong electrolytes, it must completely dissociate. That tells me we have to be here with our equilibrium constant. It's definitely going to be favorable, and we're going to have none of our initial molecule left over. So an example would be HCl, gas, dissolving in water. And I'm only going to draw a forward arrow because the KEQ is very much greater than 10 to the power of 3. And I'm saying that all that's left when you dissolve this in water is this hydronium ion and chloride anion. For partial dissociation of a weak electrolyte, our KEQ could be less than 1, or anyone all the way down here. So our KEQ is going to be less than 1 in the, let's write it this way, we're going to be here. In the in-between stage, specifically the less than 1 stage, because we're not going to get very much product. So take HF gas, for example. If you try and dissolve that in water, you will find that only a little bit of it actually gives you hydronium ions and fluoride anions. Most of it's going to stay as hydrogen fluoride gas. So specifically the KEQ less than 1. But above the 10 to the minus 3. So we're in this gray area. So the reaction still proceeds, just not very much. So now you can complete question 4. Please pause the video to try that out. And I will go over the worksheet questions in a separate video, by the way. But after you've tried those questions, we can now define acids. So acids are basically a specific type of electrolyte. So if we look at the Arrhenius definition of an acid, it's any electrolyte, which we've already defined, that contains one or more hydrogen atoms and produces H3O plus ions in water. So that means acids, since I know what an electrolyte is, acids must carry electrical charges. They could be molecular. They could be ionic. For Arrhenius acids, they're going to be molecular. So these are the exceptions. This is where that sometimes molecular comes in. There's a second definition of acids, considered an umbrella term, called a Bronsted-Lowry acid, which was just defined as anything that donates a proton. So an Arrhenius acid can be a Bronsted-Lowry acid. But a Bronsted-Lowry acid can't necessarily be an Arrhenius acid. So if we can also then define strong acids and weak acids, just like we define strong electrolytes and weak electrolytes. A strong acid is something that dissociates extensively to produce lots of H3O plus ions. So again, we are saying KEQ greater than 10 to the third. For weak acids, it only partially dissociates when we're saying KEQ is somewhere between 10 to the minus 3 and 10 to the third. Just like we did here for strong electrolyte versus weak electrolyte. And that should make sense because acids can be a specific type of electrolyte by the Arrhenius definition. So knowing that, Now please pause the video and go and try question 5 on the worksheet. Now this page comes from the worksheet. So in the worksheet, I asked you to write out the equation, the chemical equation for sulfuric acid losing the maximum amount of protons, and you had tables that you could refer to. And I also asked you to show the balanced chemical equation for the maximum amount of protons lost by phosphoric acid. Here I'm showing you a breakdown. So what we're looking at is, if you didn't have the tables in 12a and 12b, how do you determine a weak and strong acid? Well, if we go back to the definitions, you know what happens and what doesn't happen, but how do you know to write that out? Well, you have to figure out the equilibrium constants. So if I don't give you a table, but instead I give you the equilibrium constants, you could tell me if the acid that's being dissociated is weak or strong. A note here, you might see equilibrium constants of acids specifically written as Ka. So this is the equilibrium constant of an acid. Constant of the dissociation of acids. So you might see Ka instead of Keq. Still an equilibrium constant. So in the case of H2SO4, what I did here was I just split up the loss of each proton on H2SO4. So H2SO4 has 2 protons. It loses one at a time. If it loses 1 proton to water, you get a hydronium ion, and then what's left over is HSO4 minus. The equilibrium constant of this reaction is greater than 1 times 10 to the 3rd. That tells me H2SO4 is going to completely dissociate one of its protons and form only hydronium and HSO4 minus in water. Now I'm just going to look at HSO4 minus. So what H2SO4 turned into. Let's say I have a bunch of this. I put just this in water. If we look at what's happening here, so this is the first one. We have another little vial here of just H2SO4. And this is water. As I pour this in, I should see only HSO4 and no H2SO4 in solution anywhere. Because I know that this is a strong acid, it's going to completely dissociate. Now if I have another beaker that has HSO4 in it, and I'm putting that into a beaker of water, according to this chemical equilibrium, it's 1.2 times 10 to the minus 2. That's a KEQ that's less than 10 to the minus 3. This is not going to fully dissociate. This is going to be a very weak acid. You'll maybe see 1, but you're going to see a lot of HSO4 minus just hanging out in solution. Maybe one of these in one of these. So right at the edge of the cutoff. Now for phosphoric acid, on the other hand, we have to put in the equilibrium arrows here. The equilibrium constant is 10 to the minus 3. So we're going to get a little bit of product, but more reactant. Now we're at 10 to the minus 8. We're way down there. This reaction probably is not going to go. So for all intents and purposes, you might see that, but probably not. It's not going to happen. And 10 to the minus 13, just no reaction there. So right off the bat, we can just state that phosphoric acid and any of what it turns into, since it can lose 3 protons, here it lost 1, and then if I have a solution that's just H2PO4 minus, I try and put that in water, I lose the second proton. I try and put HPO4 2 minus in water, and I lose the third proton, but these are all extremely weak acids based on their chemical equilibrium constants. Hopefully this is a little bit clearer. If you still have questions on this page, let me know. We're just trying to highlight how chemical equilibrium relates to, one, the arrows, which you've already talked about, and how it relates to whether you distinguish a strong acid versus a weak acid. And some acids, since they can lose multiple protons, can go from strong to weak, or they stay weak the whole time. I think there are rare occasions when they are strong the whole time. Alright, so we have covered what an electrolyte is versus a non-electrolyte, what a strong electrolyte is versus a weak electrolyte. We've covered what an Arrhenius acid is, what a Bronsted-Lowry acid is, and a strong acid versus a weak acid. So now we're going to move on to defining bases. So an Arrhenius base, just like an Arrhenius acid, is an electrolyte. But now it contains a metal ion and a hydroxide anion and produces OH- when it's dissolved in water. Bronsted-Lowry base is anything that accepts a proton. So again, an Arrhenius base could be a Bronsted-Lowry base, but a Bronsted-Lowry base is not necessarily an Arrhenius base, because OH- will gladly accept protons. So pause the video, try and define strong base versus weak base, since you've already had some practice defining strong and weak electrolytes, strong and weak acids. So a strong base should have a similar definition based on what you've already seen. If it's strong, it should dissociate completely into to give hydroxide anions in water. While a weak base only partially dissociates. Pause the video and tell me, if you haven't already, what the chemical equilibrium constant for a strong base might look like versus a weak base. And yep, for a strong base, again, we want full dissociation, so that KEQ better be above 10 to the third, above or equal to. And if we're weak, we're somewhere in that gray area. So below 10 to the third, but above 10 to the minus third. And in that less than 1 phase. Alright, so with this information, you can complete questions 6 through 8 on the worksheet. One last thing, typically Arrhenius acids are strong acid, or bases, excuse me, are strong bases. So since we're dealing with metal ion and hydroxide, a note on that should sound familiar. This is going to be an ionic compound. So solubility rules apply here and could help you figure out whether or not something's going to give off an OH minus if you put it in water. All right. So questions 6 through 8, you guys looked at this idea of Arrhenius acids and bases. Again, watch the video if you have, for the worksheet that I will post if you have questions on that. We are going to move on to the section 7, the auto dissociation and KW. So this is dealing specifically with water by itself. We're going to look at water and some neat properties that it has. So on this page, I'm just recapping what we currently know about water. So we know here that we define an acidic solution as 1, right? So we defined an acid as something that gives off protons. So it makes sense that an acidic solution would have a higher concentration of hydronium than hydroxide ions in it. So if we had an acidic solution, got some water molecules around because that's our solvent. We got some OH and some H3O plus, but we have more H3O plus than OH for it to be considered acidic. For a basic solution, we have more OH. Than H3O plus concentration. Now for a neutral solution, so neutral water, we have something a little strange. You would think a neutral solution would have 0 hydroxides and 0 hydroniums, but that's not the case. It actually has equal amounts. OH minus, H3O plus. So for auto dissociation and KW, we are going to look at this phenomenon, how water can actually dissociate itself. That's what auto means. And it has a very special equilibrium constant. So go ahead and try questions 9 through 10 on the worksheet. It's going to give you some background. and pause the video, and when you're ready, we can start it again, and we will summarize questions 9 through 10. So question 9. We learned that the equilibrium constant for the auto dissociation of water Alright, so auto dissociation of water, which this you also had this in your worksheet. So it's where water can actually protonate and deprotonate itself to give you this. So here water is both the solvent and the solute. If we write an equilibrium constant, the products over reactants raised to the coefficients, we get this. And if we do a unit check, we're talking about concentrations, and we will see we have molar for OH, molar for H3O+, and then divided by molar squared for water. And that shows me that these are all going to cancel out, and for Kw, or K, the equilibrium constant of water is unitless. Auto dissociation of water. But we learned something else in the worksheet. We learned that H2O concentration is so large that we consider it constant. Therefore, it becomes part of KEQ. And we said that this H2O with KEQ is now called KW. So if we've pulled out the H2O for question 10, our new equilibrium constant for the dissociation of water is Kw, which is just equal to the products multiplied by each other. This is a pretty important concept to remember, and it's one of the many things that makes water so unique. So you can now go ahead and complete questions 11 and 12. Pause the video, and then you can come back and we will figure out what the dissociation of water actually is at 25 degrees Celsius. So based on the worksheet, and also based on what we know here, on page 7 of the lecture notes, we said that the concentration of hydroxide equals the concentration of hydronium, and that we've determined that that value is 10 to the minus 7 molar for each of them. We should find that Kw, if we plug those values in, so this is at 25 degrees Celsius, 10 to the minus 7 molar for NaOH times 10 to the minus 7 molar. When you multiply exponents, you actually add them together, so we get 10 to the minus 14 molar squared But remember, we said that this was unitless because that molar squared is now in the unit itself. So it's just 10 to the minus 14, no units. Because the equilibrium constant for water is unitless. Show that right here. So this is always the value for Kw at 25 degrees Celsius. No matter if the concentrations of OH minus or H3O plus change. So we could look at some trends. If OH minus is equal to H3O plus, then what is Kw? Hopefully you wrote down 10 to the minus 14, based on what we just said, that it is always that value at 25 degrees Celsius, and that's the only temperature we are looking at this semester. What about if OH minus is greater than H3O plus? Then Kw equals 10 to the minus 14. Doesn't matter if the concentrations change. If one goes up, then the other one goes down proportionally. And what about if OH minus concentration is lower than the hydronium concentration? Yep, you guessed it. Should be 10 to the minus 14 for the equilibrium constant. So the other thing you want to remember is this. Alright, second to last section, pH scale. So the pH scale is just a different way to report the concentration of an acid. Or, in other words, the concentration of H3O plus ions in solution. So instead of just talking about molarity of H3O plus, we have these equations that can tell us the concentration of a solution, the concentration of acid in a solution. So this only talks about acid. So this equation right here, we're saying this is how to calculate the pH from a known hydronium concentration. If you rearrange this, so this is the negative log base 10 of the concentration. If you rearrange this, so the opposite, just like addition is opposite subtraction, a log is the opposite of 10. So log base 10, which we just write as log, is the opposite of 10 raised to some power. This hydronium tells us the power we raise it to, and so here we've rearranged it to tell us how to calculate hydronium concentration from a given pH. These equations and the pH scale itself tells you nothing about OH concentration directly. So if you remember, when we talked about going from grams to atoms, you have to go through moles. Grams to moles to atoms. You can't convert directly from grams to atoms. Similar concept here. If you know the pH, you can go back and forth between pH and concentration of hydronium using these equations right here. You cannot go from pH to concentration of hydroxide, but you can go from hydroxide to hydronium with Kw. So this is important to remember, just because. So we'll see what the actual scale is, but you can now complete question 13 in your worksheet, and then pause the video, do it, and then we'll give a quick summary. So based on what you've calculated in your worksheet, what pattern did you see emerge around the pHs? Hopefully in your calculations, you'd see that if the pH is greater than 7, then that meant that the concentration of the hydronium, it's going to get a little weird, less than 10 to the minus 7. So pH greater than 7, so some examples, we'd go to 10 to the minus 8. Remember, negative numbers, the bigger you get, the smaller they are. And that meant, so pH greater than 7 meant that the hydronium, the acid, has a very small concentration, so we would call this basic. So by inference, I can infer that the concentration of hydroxide is much bigger. I don't know what it is. I need to convert concentration of hydronium into hydroxide using Kw. If the pH was equal to 7, then the concentration of acid equaled 10 to the minus 7. And as we learned on the previous page of the notes, when the acid equals 10 to the concentration is 10 to the minus 7, I have a neutral solution. And I can infer that the base concentration will be 10 to the minus 7, because 10 to the minus 7 times 10 to the minus 7 equals Kw. You have to use Kw to find out the concentration of the hydroxide if you're working with pH. And lastly, if the pH is less than 7, that means the acid concentration is really high. It's greater than 10 to the minus 7. So remember, with negative numbers, again, the smaller the number gets, the lower in value the number gets, negative 6, 10 to the minus 1, your actual value is getting bigger. And that tells us we have an acidic solution, and the concentration of acid is high, therefore the concentration of hydroxide or base is low, to find out what that number is, I need to use kW. Alright, the last section. This section, when we go over it, I'm giving you a very brief overview. This goes a lot more in depth, but unfortunately we don't have time to cover it in depth this semester. If you're taking 109, this will be covered more in depth. You might want to go to professor's office hours just to make sure that you're understanding how these work. But I'm giving you the basis on understanding the components of buffers. So the key thing about buffers. A buffer is a solution that resists changes in the pH. So if you have a solution that's acidic and you try and add more acid, if it's a buffer, it's not going to increase in acidity. So it resists changes in pH. The reason it doesn't change pH is because it contains either a weak acid and its conjugate base. We're going to define conjugate in a minute. Or this solution contains a weak base and its conjugate acid. The fact that it contains either of these is what allows the solution to be a buffer. It has to be weak, acid or base. Let's define some conjugates. So a conjugate, if you look up the definition, is a synonym for the word couple or married. And in chemistry, we call an acid plus its conjugate pair, conjugate base, we call these two things conjugate pairs. Now, conjugate pairs differ from each other by only one proton. So this could be an acid and its conjugate base, or a base and its conjugate acid. This is also considered a conjugate pair. But the key thing here is that they differ by only one proton. So try completing question 14 in the worksheet. I'll give you one example. So an example here would be H2O and OH minus and H2O and H3O plus. So this was an acid. It donated a proton. And this is its conjugate base. Here, this is water. One of water's unique properties. There's a few other molecules that can do this. Water can act, as we've seen, as both an acid and a base. Here, water accepted a proton to become an acid. Conjugate acid. So another key thing is whatever you start with, the conjugate of that is always the opposite. So if you start with an acid, the conjugate will be a base. If you start with a base, the conjugate will be an acid. And again, they differ by only one proton. This has 2 protons, this has 1, this has 2 protons, this has 3. Alright, that is chapter 15. Finish up that worksheet. I'll post the answers to the worksheet shortly, and hopefully you guys all have a great weekend. See you Tuesday for chapter 16 and a review session. Please bring pointed questions to the review session.